Hello, I'm Yasha. I'm from Bar-Ilan University, Israel. You're going to watch a series of lectures on philosophy and methodology of science. As an example, we're going to go through low temperature measurements of superconductivity. The major steps involved in conducting experimental study: identify and define the problem. This is your scientific background, your personal scientific interest. This is your area you come from. It could be engineering, physics, any exact science. Then you have to review the relevant literature to understand what experiment is needed to compare what has been done. It can improve your methodology to understand what other research groups are doing. After that, you formulate your hypothesis. This is your exact problem, what your research is about. You have to define your goals and precise questions to answer. Then the most time-consuming and challenging part is constructing experimental design. This is where you have to understand how you're going to conduct your research, to design the whole part of the problem. Then you go and conduct your experiment. After you've conducted the experiment, you take your data, analyze it, and present it in an understandable form. Then you present your findings and conclusions. In many cases, in experimental research, you might go to those steps several times, because you might find something unexpected. Then you might need to improve your methodology or your experimental design, or you might find that something you wanted to measure is not measurable at all, or the technology is not invented yet for this. So our background here is the superconductivity. Let's understand first what it is. What is superconductivity? Superconductivity is a phenomenon of exactly zero electrical resistance and expulsion of magnetic flux. It was discovered by Dutch physicist Heike Kamerlingh-Onnes in 1911. Exactly zero electrical resistance, it's like throwing a rock in space. It will flow there forever because it's in no resistance at all. And magnetic flux expulsion, that means magnetic field cannot enter a superconductor. To understand how this research be beneficial to science, we need to understand where it's used. The basic superconductivity applications are high field magnets. When you put a current in a coil, it generates magnetic field. It is possible to create a very big, huge magnets, for example, for particle accelerators in CERN. It is possible only with superconductors. The most famous application for superconductors is MRI, magnetic resonance imaging. Superconductors are used there to create a high magnetic homogeneous field to interact the matter of our body to create those images. Magnetic levitation. The expulsion of magnetic field from the superconductor generates the force. It allows to create high-speed maglev trains which are actually floating above the surface and reduces a friction between the rail and the train. A superconducting magnetic energy storage. If you have a superconducting coil, it generates a magnetic field. Some energy is stored in this magnetic field, and if we close this switch, we can make this current dry forever in this coil. And when we need this magnetic energy, we open the switch and we drain the energy when it's needed. And probably the most obvious one is the superconducting cables for power transmission. around 10% of generated energy is wasted in the transmission lines due to resistivity of copper or aluminum cables. By replacing those to superconducting cables, we can save billions of dollars annually worldwide. That's why the research on superconductivity is very beneficial in engineering and physics applications. But let's understand what's the basic parameters of superconductivity. The critical temperature. Superconductivity happens only below a critical temperature, which might be very low for humans at least. Above this critical temperature, a superconductor behaves as normal or even very bad conductor. You can see this transition from normal state to superconductor state, where the resistivity drops to absolutely zero. The critical current, JC. The absence of resistivity in superconductor doesn't mean that you can put any current in it. There is some limit to it, and that's the critical current density. It depends on temperature, on type of superconductors, on many other things. And critical magnetic field, BC. Magnetic field destroys superconductivity. Above the critical field, the material behaves like a normal conductor. Magnetic field also reduces the critical current. So when we design a coil or magnet or whatever it is, we need to clearly understand what type of superconductor is used. Those three parameters generate what's called a critical surface of superconductor. A critical current density, JC, critical temperature, TC, critical magnetic field, BC. Below this surface, the superconducting material is in a superconducting state. Above it, it's normal materials. This is all beautiful, but superconductor has zero resistivity only in static magnetic fields. When the current and/or magnetic field change in time, energy is dissipated in the superconductor. For example, in the SMAS, the energy storage device, when we charge or discharge our SMAS, some energy dissipation occurred. This energy dissipates in terms of heat. It heats the superconductor and change its parameters because the temperature might change and so on. So this research is crucial for designing the superconducting applications where some alternative currents or fields are involved. There are many types of superconducting materials. These are the main ones. You can see the critical temperature are very different from one another. The cost, of course, it's also different. We are going to focus on the MgB2, magnesium diborate, the last one. MgB2 was discovered in 2001. It has a critical temperature of 39 Kelvin, and it has a pretty decent current density at 10K in zero field of 10 in power of 10 ampere to meter square. So let's identify our research problem. After deciding the topic of interest, superconductivity in our case, the researcher must define the research problem. This helps the researcher to focus on a more narrow research area to be able to study it appropriately. Defining the research problems helps you to formulate a research hypothesis. In the research process, the literature review stands as a pivotal point of all activities. The researcher must clearly understand what has been done already, what kind of research would add to a body of knowledge in this area. The researcher might not understand the whole process, the whole work that has been done by other research group, but he needs to clearly understand the direction of his research. After it's done, researcher must formulate the hypothesis, the actual objectives of the experiment. In our case, the research question is, in what way energy losses in wires made of magnesium diboride superconductor depend on frequency, current amplitude, and temperature? The next talks will focus on aspects of investigation of the energy loss in magnesium diboride superconductors. Thank you.